So here we are going to talk about the efficient data pipelines. This is introduction. So the main idea is when training AI or AI models, people often think training is slow, and therefore they should buy stronger GPUs. But many times the real problem is the GPU is waiting for data. The GPU is extremely fast, but if the CPU or data pipeline cannot prepare data quickly enough, the GPU becomes idle or not busy. So let's talk about understanding the data pipeline. Training data moves through these paths from storage or disk to CPU data loader to GPU to model training. So the goal is to keep the GPU busy all the time. If the GPU waits for data, training slows down, hardware is wasted, experiments take longer. What is a data bottleneck? Imagine GPU can process 10 images at once, but data loader only provides 2 images fast enough. So the result is downgrade of GPU's usage, the training speeds become slow, the efficiency is not effective. This is called data bottleneck. The bottleneck is not the GPU power, but the bottleneck is slow data loading, slow CPU preparation, slow disk reading. So here's the PyTorch tools for data loading. PyTorch mainly uses dataset. The dataset classes defines where data comes from, how one sample is loaded. It is the blueprint of your data. And the data loader is it creates the batches, shuffles data, loads data in parallel, feeds data into the GPU. Here's the important dataset methods. A custom dataset usually contains init method. It is used to load file paths, initialize variables, prepare dataset. While the length is it returns the total number of specific samples. Like for example, it returns 50,000 samples, and here's the get item index. It loads one sample. Example, we have the image and label is equivalent to dataset, and the index value is 5. This is the core method used during training. This is important data loader parameters. The batch size, it controls how many samples are processed together. Example, if we have the batch size of 32, it means 32 images processed at once. Larger batches means better GPU utilization. There is no waste GPU's core. So it has a faster training sometimes. If it's too large, GPU memory overflow. Let's say we have the shuffle equivalent to true. It randomizes data every epoch. Why it is important? Without shuffle, model memorizes order, overfitting risk increases. With shuffle, better generalization. And what is number of workers? Very important here. It controls how many CPU worker processes load data in parallel. Example, we have the number of workers 4, meaning there are 4 CPU workers prepare data simultaneously. Why the workers matter? Let's say we have the number of workers 0, that's the default value. This means only one process loads data. The problem is GPU becomes idle. CPU cannot prepare batches fast enough. Here's a restaurant analogy. Let's say we have one cook, orders pile up, customers wait. If we have multiple cooks, orders prepared simultaneously, restaurant becomes efficient. Same with data loader, more workers, faster batch preparation. Next is experiment. Let's say we have the number of workers 0 to 10. Using the CIFAR 10 dataset, we have the multiple epoch, and we measure the average epoch time, meaning how long one full training pass takes. And important finding, it increasing workers initially, it reduces training time, especially from 0 to 2 workers. That's a huge improvement. But after some point, gains plateaued, meaning adding more workers stop helping much. Why too much workers become bad? Each worker consumes CPU resources, memory, disk I/O or input output. Too many workers causes competition, overhead, context switching. The result, performance can stop improving or even become worse. So here's another analogy. Let's say we have the 2 to 3 cooks, that's efficient kitchen. If we have 20 cooks, it's chaos, collision, resource fighting. Same idea with CPU workers. So here's one of the important key concept here is the diminishing returns. So here's a major optimization principle. More is not always better. After optimal point, extra workers added overhead. There's extra works. Efficiency stalls. This is called diminishing returns. Next is GPU utilization. So it showed the blue means is active GPU work and the yellow is GPU idle time. When workers increase, GPU idle time decrease, and GPU stayed busy longer, meaning better efficiency, faster training. But after around 46 workers, improvement stalled. Next is main optimization philosophy. Before upgrading hardware, first optimize data loading because hardware will already be powerful enough, and pipeline inefficiency may be the true issue. Next is rule of thumb for number of workers. So it suggests that start near our CPU core count. Like for example, if CPU has 8 cores, try maximum of 8 cores. Like for example, it start in 4, 6, and 8. That's a benchmark. Let's focus on trends, not exact numbers. Performance fluctuates because of shared cloud resource, operating system scheduling, caching, disk activity, and server allocation. So exact milliseconds are not important part. The important part is the trend. Like for example, we have the 0 workers and slower than 2 workers. That trend matters. Next is metrics we should monitor. So it recommends main metric, average epoch time, because it directly measures training speed. And secondary metrics is GPU utilization, CPU usage, memory usage, and disk I/O. This help locate the bottlenecks. Next is core principle of the entire things that we have discussed is efficient training is about balancing the pipeline, not maximizing the workers and maximizing the hardware, but feeding the GPU consistently without overwhelming our CPU resources. So its most important concepts to remember. The key takeaways here is first is slow training is often a data problem, not always a GPU problem. GPU should stay busy, idle GPU wasted performance. Number of workers controls parallel data loading. More workers, faster loading initially. Too many is overhead increases. And find the saturation point. Best performance happens at optimal balance, not maximum workers. Focus on trends. Benchmarking always varies slightly. Interpret patterns, not exact values. So here's the simple real-world summary. Think of it like training like a factory. Like if you have the CPU workers, we supply workers, and GPU means this is the machine. If supply workers are slow, machine waits. If too many supply workers, factory becomes crowded. Best performance is smooth and balanced flow.